Oh,
All right, welcome everyone to another video. In this video, I'll be teaching you how to make a buck converter, making use of this current mode chip, you know, UC3845. There is the UC3842, 43, 44, 45, but I'm using 3845, and their major differences is that UC3845 can do 50% duty cycle maximum, while 30 3842, 3843 can do up to 100% duty cycle. 44 and 45 can do up to just 50% duty cycle. Anyway, I'm using 3845 for this particular design, and I'm just going to give you an overview of this, and then of course show you how to wind the transformer. There are tricks, you know, involved in winding this chopper transformer successfully. All right, now I'll follow the video through, and please, it's been a while I did the video. It's really not easy putting content together like this, so you may do well to subscribe in order to support us as we continue to do this good job. Anyway, um like I said, I'm going to show you how to wind this, and then let me just quickly explain how this whole circuitry works. What we have is, an input. By the way, I'm designing an inverter. It's a 48 volt inverter, but inside your inverter, you still need to power some other things, like your fan, your driver circuit, the microcontroller that will be used, and all of these things work with different voltage levels. All right, so there needs to be a way to efficiently step down your 48 to 60 volts down to around like 15 volts, and 12 volt for fan, 15 volt for your driver circuits, and then I think another, yeah, of course, 5 volts for the microcontroller. So all of this conversion needs to be done efficiently, of course, because you are using a battery input. And one of the consideration is your input can rise to up to like 60 volts. All right, that's just by the way. Anyway, so how does this circuit work? This is the chip, and the power supply for the chip is fed to pin 7. All right, so this your arrow, your startup resistor. In order to calculate it, the minimum startup current required for this chip to start working, all right, is, I think from the data sheet I got, around 30, I saw around 13 milliamps. All right, so for you to get this value, that's why there's no fixed value. It depends on your design. For this value, what you use, remember, V, this is a very beautiful formula. V is equal to IR. So assume we're doing 60 volts, but we will not use 60 volt because we want it to also start up when the voltage has gone below 60. So let's assume we want to use our low voltage threshold as a reference point. So assume it is let's say 40 volts input. So you just say 40 is equal to I, which is 13 now, 13 divided by 1000. Then of course your R, which is your startup. Okay, so if you cross multiply, we should have something around this is, let's say, 40. Am I using 40 now or 44? Okay, 40,000 all over 13. That should give you the value of your startup resistor. Okay, so I just thought I should explain that. Then, so whatever value you get there, you put it here in your circuit. So this sends the initial current for this guy to start up. All right, then once it starts up, the auxiliary takes over from there and start powering it up. Okay, so but it needs to start up in the first place. Now the frequency of oscillation is given by frequency equal to 1.72 over RTCT. RT is your timing resistor, and your time, this CT is your timing capacitor. Here I'm using 0.001 microfarads, and for the timing resistor, I'm using 22 kilo ohms. So if you plug in all of that, it gives you the switching frequency. But one thing to note is that whatever value you have here, you divide it by 2 because it's 3845. The output features a totem pole, and your totem poles output will divide the frequency into 2. So at the end of the day, what you get at your output, which is pin 6, will be half of whatever you calculate here. All right. Now, um, the frequency is set by the two of them, like we said. And then we have pin 3. What does pin 3 do? It senses the current, between the drain and ground. Sorry, this is your source. Between the source and ground, this is the drain, this is the gate. All right. So when switching is going on, it's monitoring the voltage across this low value resistor. So what happens is, if it rises to around 1 volt, it will send a signal to pin 3. Pin 3 would adjust the output duty cycle so that you don't damage this MOSFET. All right. By the way, I'm using IRF 640N. Okay. This is your pull down resistor, 10K, needed to pull it down when it is not switching. And what else? Yes, you use a bypass capacitor to reduce noise in your circuitry. But of course, this 100 microfarad, 100 volts capacitor is needed here to store enough charge to keep this guy running. Okay, then this is your feedback system. We have 100K between pin 2 and pin 1. Then, but of course, this is the feedback at the output. So what it does is it checks what's going on at the output and make sure it's stabilized depending on the wiper position of this variable resistor. Well, I think those are the major things. If you have any other question, feel free to drop it on in the comment section. I would make our time to answer as quick as possible. Yeah, this is your secondary. A capacitor needs to be here to store charge for stable output. Like I said, you have more questions you may ask, but then the next time we'll be meeting, or after now, I'm going to be showing you how to wind these transformers. They're called chopper transformers, or high frequency transformers. Okay, they are quite tricky to wind, but if you get the hang of it, you can be able to be successful with winding them without glitches. All right, so that's how the circuitry works. I'm going to show you how to wind this pretty soon. See you soon. All right, welcome back. Earlier I had explained how the circuitry works, and so now I'm going to just show how this the ferrite core transformer is wound. Like I said, there's a trick involved, and if you don't follow it correctly, it just won't work. All right. Now, in this video, I'll try to show you the calculations involved in knowing the number of turns to wind for the specific design you have. Like I told us, what we are going to be designing this for is like a 60 volt input. All right, and of course, the battery voltage can drop as low as 44 volts thereabouts. Okay, that will be our low battery cutoff. Anyway, 60 volts. Okay, it will rise to around that 60, maybe 58, 59 thereabouts, while the battery is charging. So I'm just going to show you, like I said, how to do the winding. It's quite simple, but if you don't know the technique, it will just not give you the result you are looking for. So we have 3 windings here. You can add other windings if you want, but for this one, I think I'll do an extra winding anyway. That extra winding will be for fun, while this one of the windings on the secondary side would be for the driver circuits and some other parts of the circuit. Now, this is the first winding, this is the second winding, and this is the third winding. Now we want a situation where even if the battery drops down to its around the low battery threshold, you should still be able to have um, enough voltage at the output. So what we're going to design this with is assuming the battery has dropped down to around 40, let's say 42 volts. So um, we have the primary, we have the auxiliary, and we also have the secondary. By the way, this whole setup is known as a flyback topology. Flyback topology. Now, flyback topology simply means that the secondary windings usually get output when the primary is off. All right. So what happens is, if the voltage is applied here, current flows through this. Remember, this is a MOSFET, so it will act like a switch here. Drain connects to source. Through this guy flows down. Drain connects to source through this resistor down to ground. Down to ground. So when that happens, a flux is generated here. By the time it switches off, that flux collapses back into the auxiliary and the secondary. All right, and then you now have voltage appearing across this and across this. So it just keeps happening like that over and over again. All right. Now how do we calculate for the number of turns here, here and here? The formula: number of turns of the primary, because that's the one you calculate first, is equal to um, Vmax times 10 raised to power 8 all over 4 times Bmax, which is this Bmax is your flux density, times core area, which I would denote as this, and then your operating frequency. All right. Now, if you plug this in, you get the number of turns. Of that, if you plug in all the values for all of this. All right. Already we know that our Vmax, that's the maximum voltage. We're expecting about 60 volts when it's charging. So let's say 60 is our Vmax. Then Bmax, usually you can use a value between, I think, 1000 to 2000 Gauss, but I like being in between, so I normally use 1500 Gauss. All right, that's for our Bmax. Then core area. All right, the core area would be, now let me just say this, the core is the area around which you do your winding, and then this is the core because this is the area around which I'll do my winding. All right, so we'll just get an approximate diameter of this. It's a circular core, so let's see, this is around 1 point, let's say 1.2, the diameter of the core. Since it's circular, diameter is 1.2 centimeter. That means the radius is 0.6, I think 0.6 centimeter. So remember, the area of a circle, area is pi radius squared. All right, so our core area becomes what, pi into 0.6 squared. So what do we get? Core area, we have pi. Where do we have pi on this calculator? Okay, pi into 0.6 all squared. What will that give us? 1.13 centimeter square. So this is our core area, this is our flux density, maximum flux density, and then the frequency. So sorry, there was an error in the calculation earlier. All right, frequency would be 1.72 divided by our timing resistor 22k, which I've already started here. So this is the value 22k, 22,000 times our timing capacitor. The value I used was 0.001, which has a code of 102 times 0.001 microfarads. So this is 10 raised to the minus 6. So I'll take it up to be 10 raised to the power 6. Basic mathematics. 1, 2, 3, 3. So I have 1720 divided by 22 times this should give me 0.22 times 0.001 should give me 0.022. So let's see what this will give us. 1720 divided by 0.022. So we get approximately 78 kilohertz. But remember, like we said earlier, it's going to be divided by 2 because of we're working with 3845. So if we divide this by 2, 78 divided by 2, this should give me let me use my calculator. 78 divided by 2, I get 39. So the frequency we are working with is approximately 39 kilohertz. So what we'll now do is, since we have all the values, we have the value for frequency. The core area is 1.13 all squared, and then we have our B max, which is 1500, and then let's just plug in the values and see what it gives us. So the number of turns for the primary would be V max, which is 60 in this case, 60 times 10 raised to the power 8 all over 4 times B max, which is 1500, times core area is 1.13, times our frequency is 39,000. So let's see, 1, 2, 3, 4, 5. This gives me this. Okay, let's move on from there. We have 60,000 divided by 4 times 15 times 1.13 times 39 gives us 2644.2. So a number of turns for primary would now be 60,000 divided by 2644.2. So we have about approximately 20, let's just say 23 tons. 23 tons. But I like taking it to the nearest zero number, or the nearest zero number. So this would give me approximately 30 tons for the primary. Now for the other ones, we want this guy to always be on when switching is going on. So because of that, we can say, the voltage we want here at every point in time should be around let's say we want it to always have 15 volts. and we want our output to always have around so this is for auxiliary, and then we want our output to always have, let's say, 17 volts 17 volts for the secondary. So what we do is this. Now we already know the value, the number of turns for primary. Primary turns is around approximately 30. Primary is 30 turns. All right. Now, if 60 volts, so I'm not going to use this one now. Let's just use the exact value we calculated for, and you get to know later. 23 turns. If 60 volts is giving us 23 turns, then 15 volts would be how many turns? So if you cross multiply, you have 15 times 23, 15 times 23 divided by 60, so we get 5.7, 5.75. So if we take that to the nearest whole number, or the nearest whole number, what that will give us is around 6 tons. So 15 volts would be around 6 tons. Then if we want 17 volts, we'll do the same thing. 60 volts gave us 23 tons. Then 17 volts would be 17 times this divided by 60. 17 times 23 divided by 60. So to the nearest whole number, that gives us around 7 tons. So this would be around 7 tons. All right. Now I'm going to do 6 tons for auxiliary and 7 tons for the secondary. All right. But now, one thing we need to know is the way you do the tons. Now, if you look closely in the circuit, you find out that there are dots here. It's called dot convention. Okay, these things are very important. If you don't follow it correctly, it's going to be wrong. Now we know that for this primary, we are doing 23 tons, so, or let's say 30, nearest zero number. Then for the auxiliary, we have 6 tons. So I'll just say, let's say, okay, 6 tons. Then for the secondary, 7 tons. Okay. Now, how do we do the winding? This is very important, so listen closely. If I want to wind this now, since I know it's going to be 30 tons, the first thing I do is I usually start my winding from this one. Then I go around, divide this by 2, that gives me 15. I'll go around 15 times, following this direction, 1, 2, 3, 4, 5, 6, 7, till you get to 15. You stop, close it with masking tape. All right, maybe 2 layers or thereabouts, or 3 layers of masking tape. Then the next thing I do is I now do my secondary next. But when I do the secondary, I will still make sure that I do everything in the same direction. So I'll start here and wind around. Secondary will be 7 tons. I'll do 7 tons. But by the way, take note that before you do the winding, you should use a thick wire. But the thick wire should be made up of tiny ones tied together, so that you can get enough current out and you can avoid what we call the skin effect. All right, thick wire made of thin ones. Okay, then you go round following the same direction. All right, when I'm done doing the 7 tons, I will close it. Then I'll come back to the primary and complete the remaining 15. When I'm done with that, I'll close it with another like 3 layers of tape. Then go back here, yes, I'll come back here, following the same direction. Also, I'm going to do the 6 turns for the auxiliary. After doing that, I close everything. But now, this is where you now know how you connect it to the circuit. My start of the turn, the start, like, remember, this was where we started from, would be this. The end, at the end of the day, for the primary would be this. Then this also tells you that wherever I started the auxiliary will be ground, and the end will be this part. The same way for the secondary, where I started my winding, make sure, like I said, for all of them, let them follow the same winding direction. Where I started this secondary will be what will go to ground on this side. Then the end is what will connect to this diode and the rest of the circuit. If you don't do it exactly like this, it won't work. So please take note of that. I hope this is able to throw lights on winding chopper transformers. If you have questions, please feel free to drop it in the comment section. I'll take our time to answer them. Thank you so very much for watching, and please, if this helps you, kindly subscribe to our channel so that we can be encouraged to continue to do more of this kind of contents. Thank you so much, and please refer your friends to this channel who you know this would be of help to them. Thank you once again, and see you some other time.